Good morning. So we're going to work on section 3.3, and this might seem like a whirlwind, but don't worry, you have plenty of time to rewatch these videos and do a bunch of practice problems via MyLab Math. So we come to this section because using the limit definition of the derivative is pretty cumbersome. It takes a lot of time. It takes a lot of mental effort. Maybe you have to use the conjugate. Maybe you have to do fractions and all that sort of stuff. And it can just leave a lot of room for algebra mistakes and a bunch of stuff that we don't want to deal with. So there's got to be an easier way, right? If so many people are doing calculus and using calculus in their day-to-day lives, then there's got to be a way that's easier than what we've been showing you so far. And of course there is. We would have obviously start you with something difficult and then work you into something easier, just so that you understand the foundations of it. So let's get started with that. So rules for differentiation, and there's a constant rule. So if c is a real number, then d dx of c is just equal to 0. So anytime you have a constant value, you can imagine the line of a constant value, maybe the constant value equals 1. That line has a slope of that equals 0. There's not a whole lot of changes. There's nothing really going on. It just equals 0. Next, we have the power rule. So if n is a non-negative integer, then d dx of x to the power of n is equal to n times x to the power n minus 1. So let's get a little bit more familiar with the previous two rules and do some examples. So I want you to evaluate the following derivatives: d dx of x to the power 9, d dx of x, and then d dx of 2 to the power 8. Go ahead and pause this video and work through these as best you can, and then come back and see how far you got. All right, welcome back. So at least with the first one, it's pretty clear that we can go ahead and use the power rule. So d dx of x to the power 9, we bring down our power, 9, and we put that out in front, times x to the power of 9 minus 1. We know that 9 minus 1 is 8, so we're left with 9 times x to the power 8. And if you plug this into the limit definition of the derivative, you would get the exact same answer. If you want to, you can go ahead and do that practice right now. If you don't want to and you just want to trust me, you can do that too. So let's go to the next example, d dx of x. Well, x is the same as x to the power 1, so we can pull 1 out in front, and then we're left with x to the 1 minus 1. Well, 1 minus 1 is 0, so we're left with x to the 0, and we know that x to the 0 is the same as the value 1, so we have 1 times 1. And in this case, the power rule is perfectly useful. Finally, we have d dx of 2 to the power of 8. And you might be tempted to try and use a power rule here, but we don't have anything that depends on x. It's just a constant. I think 2 to the power 8 is equal to 256, I believe, and that's just a number. So we have a slope of 0, so we know that our value equals 0. And here we're able to just use the constant rule and move on with our lives. Now, of course, you can probably see at the bottom of my screen that we're on slide 6 out of 16. There's got to be a bunch more rules. And indeed there are. So this one is called the constant multiple rule. So if we say that I've got a function f and it's differentiable at x and c is some constant value, then the derivative of c, my constant value, times f, my function, is the same as c times f prime of x, which is the same as d dx of f of x. So let's do some examples. Oh, I don't know why it's formatted like this, but okay. So I want you to evaluate the following derivative: d dx of negative 7 times x to the power of 11 divided by 8. So go ahead and pause and come back when you think you need a little help or when you're ready to see the answer. So here we're going to do our very first step, which is to pull out that constant out in front. And that constant is going to be negative 7 divided by 8. So we pull that out in front, and then we're left with d dx of x to the power of 11. Well, that's just our power rule. 11 comes out in front. X to the power of 11 minus 1 is 10. I'm left with negative 7 divided by 8 times 11 times x to the power 10. And that's the same as negative 77 divided by 8 times x to the power 10. Next, we've got sum and difference rules. So if f and g are differentiable at a point x, then d dx of f of x plus g of x is equal to d dx of f of x plus d dx of g of x. And you're probably wondering what these funny little signs are right here. That's a plus minus, and it means f of x plus g of x is equal to d dx of f of x plus d dx of g of x. But if I choose the minus sign, then I've got d dx of f of x minus g of x is equal to d dx of f of x minus d dx of g of x. It's kind of a shorthand way. Instead of writing two full equations, I get to just write one, and I get to use this little plus minus shorthand. So let's do an example. I want you to determine d dw of 2w cubed plus 9w squared minus 6w plus 4. Go ahead and pause and work this out as best you can. And if you need a little help, go ahead and continue. So we're trying to determine d dw of a polynomial 2w cubed plus 9w squared minus 6w plus 4. So I'm going to go ahead and break it up. Because we have our sum rule, I'm able to say d dw of 2w cubed plus d dw of 9w squared minus, I went ahead and pulled that minus sign out, of d dw 6w plus d dw of 4. Now I get to use my constant multiple rule and pull out my constant multiples, and I get 2 times d dw of w cubed plus 9 times d dw of w squared minus 6 times d dw of x plus d dw of 4. Our very first one turns into 2 times 3w squared. Our next term turns into 9 times 2w minus 6 times 1, because the derivative of x is just the value 1, plus 0, because we have a constant at the very end. Simplifying all that, and I get 6w squared plus 18w minus 6. And it's pretty easy to see that this would be very, very difficult and time-consuming to try and do using the limit definition of the derivative. But because we have these rules, it makes life really simple. So let's keep moving on. So this next one is not intuitive at all, and the proof is also very cumbersome and difficult to understand. So I'm just going to present you with the information, and we're going to just keep it on. So the derivative of the function e to the power x. The function f of x equals e to the power x is differentiable for all real numbers x. So we can put in whatever number we like, and we're still going to be able to differentiate this function. And surprisingly, d dx of e to the power of x is equal to e to the power of x, which is not what you would think. But just remember this, we're going to use it later. So finally, higher order derivatives. If I can take a derivative once, can I take it twice, maybe 3 times? And the answer is yes, I can take it as many times as my function will allow. So assuming that y equals f of x can be differentiated as often as we like, the second derivative of f is f double prime of x equals d dx of f prime of x. And for integers n greater than or equal to 1, the nth derivative of f is f to the power in parentheses n, that part is important, of x, and it's equal to d dx of f to the power in parentheses n minus 1 of x. And this notation is very important. If you leave out the parentheses, then it looks like you're just raising your function to a power instead of taking the derivative of that function. So let's go ahead and see an example. So find the third derivative of f of x equals 3x cubed minus 5x plus 12. You can go ahead and pause and see how far you can get. So finding the third derivative of f of x equals 3x cubed minus 5x plus 12, we get that our first derivative is 9x squared minus 5, which means our second derivative is 18x, which means our third derivative, f triple prime, is equal to just the value 18. You can imagine that if we take the fourth derivative, we would get the fourth derivative of x. We usually don't say quadruple prime, we just say the fourth derivative of x would equal 0. And if we tried to do it again to take the fifth derivative, well, that would equal 0 too. So after a point, we just can't keep taking more and more derivatives. It doesn't mean anything. It doesn't have any meaning. And that's kind of what we're talking about with taking as many derivatives as our function allows. So that's the end of this presentation. And hopefully the graphing of the derivatives and sketching of functions makes a little bit of sense. If you've got any questions, go ahead and send me an email.